Hello. Hello, hello. Welcome to my first ever stream, I guess. It's pretty cool. Um, you may have read the title, so you might know what we're going to be building today. But if you did not, then we're building a compiler in Rust, and I'm pretty hyped about it. And yeah, let's just start. So, um, I'll I guess we'll just start, yeah. So let's just create, I'll just show you my terminal, and we're gonna create a new directory. So I'd like prepared something for this stream, and we're gonna remove that. And I guess we have to sudo make that because Git doesn't like me. So let's just start from scratch here. So we're gonna make new directory, FusionLang. I'm gonna cd into that, and we're gonna create a new cargo project because we're using Rust, and we're gonna call that as gonna be the Fusion compiler. That worked. Okay, cool. And I'll just open that up real quick in IntelliJ, I guess, because I like IntelliJ. So let's just open that. Okay, nice. That works. So first thing that we are gonna do is we're gonna remove the Git repository from the cargo project, because that's just gonna destroy our Git repository one directory above. So nice. So that is gone, and now we can actually create a new Git repository here, and we're gonna set the main branch to main because I like main. And we're gonna fix IntelliJ up real quick. Nice one. Okay, now that is working. Attach cargo project. Cool. So I think we're ready to go. So first, I just want to make a quick roadmap so you know what we are gonna build, and especially today, what I want to build today. So I'll just create a quick readme using lang because we're lang devs, we like lang, and I'll create a roadmap. So for today is the 7th of April, if I'm correct. Today we are gonna build a lexer. So lexer takes an input and creates it to it transforms it to a token stream that we can work with much more easier than like with common strings or like just text. And that's what we're gonna build today. And what I want to like what should work today is something like this. What should be able to be run today? Something like this, essentially. The goal for today is to run basic arithmetic computations. So something like, I don't know, 7 plus 3 plus 7 times 8. And maybe even we could also add support for parenthesized expressions, I guess. And yeah, that's like the goal for today. So we need a lexer and a parser for that. Just get started, I guess. So we're gonna create a new package called ast. Means abstract syntax tree, which just represents the input string or input text in a tree form. to make it easier to work with. And we're gonna need a lexer in here. Okay, so what do we need? We need a token struct because we somehow have to represent our token. And our token struct needs probably a token kind because we somehow have to like switch over it. So we can like always figure out which token we're currently working with and do not have to do like string comparisons all the time, which is pretty ugly. So that would make that much easier. So token kind. And we'll probably also have to remember where our tokens are in the input file. So we can later display errors at this specific location. So that's gonna be like a text span, I guess. So text span just has a start and end and represents some span in the original input text. So let me just create an implementation for that because I like to create new functions because we don't have constructors in Rust. And we could probably also create a length function. And so now we have a text span. So which token kinds do we need? So for now, I guess we just need a number, which will actually have a already parsed integer in here. And for now, we're just gonna support integers, not floating point times. We're gonna do that later. We need plus, minus, asterisk, slash for our operators, left parent or right parent, I guess. I mean, yeah, it's right, left parent, right parent. And I think that should be it. So this needs a kind and a span. And we're probably also going to take literal for text span. I mean, we will have duplicated memory because the literal is also in the original text, input text. I guess that's fine for now. Because I don't always want to look up the original input to figure out what text the text span represents or holds. So we can just put it in here right straight away. Could probably also work with lifetimes and references and not just copy a string in here. But that's just gonna make things a little bit more complicated than they need to be right now. So now we have a text span and a token kind, and we have our token struct up and running, I guess. So we can also create a constructor for the token. Thank you, GitHub Copilot, for that. And because we are like best practice, we're gonna use self here, and probably also use that here. And we're gonna need a lexer struct now. So the lexer basically just takes something like this as an input and transforms it into these tokens that we have just defined. And for example, this would be a number token containing 7. This would be a white space token. We also keep white spaces in here. So like in the lexer, we just transform the input streak 1 to 1 into like more developer friendly format, if you want to say so. And this would be the plus token, white space once again, left parent, number, white space, plus, and so on. And that's basically it for the lexer. So not that complicated. Yeah, so the lexer is basically the easiest part. It's gonna get a little more complicated in the long run. So we also need a struct for that. Did I qualify as something here? No, we don't do that. What I like to do here is there's something called a peekable. It comes from the standard library, from the iterator library. And you can just say we want peekable and chars. So you can just pass basically any struct that implements the iterator trait in here. And it's nice abstraction that provides methods for like peeking, consuming, and stuff like that, which is pretty much what you want in a lexer. So that's pretty cool. But we need a lifetime for that. So it's a lifetime. Yep. And we're gonna create an implementation, and we also have to have the lifetime in here. Nice. Pop new. We need an input string with lifetime a. Exactly. Nice. And I just quickly want to implement the basic interface that we want to provide. I guess we could even implement the iterator trait for our lexer, because essentially what we want to have is we want to have a method called next token, which takes a mutable reference because consuming always has to do something with mutable, and we're going to return a token from that. And I guess this next token is essentially like the iterator next method, so we could do that. Let's just not do that for now. We could do that later. And if I think about it, we don't always wanna. We always want to return a token, or do we also like return null, like an option? I guess we want to return an option here, because once we have consumed all tokens, we don't want to return anything anymore. So we want to return an option here. I guess. Okay. So let's just try to parse a basic number token. We could create a little helper method here. We could say like fn is number start. It's mutable. So peeking requires a mutable reference. Yeah, that's weird. Okay. That's interesting, I guess. Okay. And we are gonna like have a method called fn peek. Change the option, and we really need a mutable reference here. Okay, that's kind of interesting. Yeah, I guess that's gonna work out just fine for now. And we're gonna say if self peek it's number start. I guess we don't. We could make the static method. So we could basically just return this digit in radix 10 because we were in the decimal system. Nice. I mean, we could say self dot. Problem is that when we say like peek here and try to do that, then we have a mutable, because this takes a mutable reference. We can probably not access self in here. We just try that. Let me think about that real quick. I guess maybe we don't want to use this peekable. I mean, it's pretty cool actually, but maybe not quite suitable for our case here. Yeah, no. Let's just take a reference to the input string. And then we also need a current pass, probably, which is gonna be 0 at the beginning. And we are gonna say like if current pass, if self at current pass is equal to, and we're not gonna return none, we're gonna return end of file. We're gonna return token new UF text span exactly something like that. Six parameters were supplied. Does it not work that way? I'm using the wrong slash. No, not. Huh? It should work. Normally. Wait, why do you not work? Okay, enough. Try. Your Copilot, help me. Wasn't that something like that? Thought it was. Okay, maybe. I think it was in Java, right? Okay. So that's a null terminating char. Okay. So I think that should work now. Expected option token. Yep. Try some. And we probably also want to increment the position here, so we don't always run back into that when we call next token. And yeah, makes sense. I'm gonna say if self current path is greater than length, then we want to return none, because then we're done. This just makes sure that we always know when we are at the end of our inputs or like token stream. Pretty much like how strings are terminated with this null terminator right here. We do the same for our token stream. And next thing that we could probably do is get our current char. So, because we could peek here. I mean, that's old because peek does not exist on our input more. Let me just actually enable analyze code on the fly, which is pretty neat. So I get errors here instead of like nothing, and then when I run the program, it just does not compile. So peek. I mean, essentially, we could not return an option here because we know that the character exists and is not out of bounds if it is called, because it's not accessible from outside and is only called by us internally, and we make sure that we are never out of bounds here. So I don't think we even need that. Yeah, I guess. So we're gonna have like a very char or something like that. And we're gonna, no, actually peek here and unwrap. Okay. So now we have to check if our current char is essentially a number, because if it is, it's gonna be the start of a number token. You could probably also do something like this. So because if we find a 3, we know that either this is just gonna be 3 or there's something more after that. And that if there is more after that, it has to fall without any white spaces, right? Because that would not be valid. It would not be 30. It would be like not valid syntax, right? But this is. So we have to check if this is a number start. So we're just gonna say let's see self current char, and we just say if self dot is if self dot is number start, and we're gonna return not some. We're gonna call something like self dot tokenize number. And why I don't want to return that directly is that we'll have to create our text span, right? And essentially, it is always gonna be the same logic for how we're creating our text span. We're gonna parse or like lex something, consume some tokens, and have a start position. Essentially, you could say let's start instead of a current pause. So it's gonna be a start, and at the end we're gonna have an end, and the difference between that is the length of the string. And so we're gonna also say literal is essentially self input start end from start to end, because end is exclusive here. And span we can just create here, and we don't want to do that or duplicate it across every single function. And what we could do, because what we need to create our number token kind is an integer, right? So we could say a number to that, and we expect that to be I64. And what we can do actually is say let mute token, or like let mute kind is equal token kind and bad. Essentially, and we have to create that bad and EOF. So I've already explained what end of file is, and essentially bad is when we reach, or if there's a token that, or like character or anything that we just cannot lex, that we don't understand. Like if I go here and just say times, I don't know, it's hashtag. What is hashtag? We have not defined what to do with hashtag. So we have to handle that somehow. And actually that's the point, because we also want to test our dividing. And now that we have parsed the number, we have to implement that method, but that's fine for now. We can set our kind. Kind is token kind number, right? And now we have like basic numbers, and we can return a token here. And now we have to implement this method, and we have to create kind of a consume method, consume char, right? And here we can not just like with current char directly, because we have here we're gonna have to return an option char, I guess, because we could run to the end of the file here. Yeah. Can we actually? Yes, we can. If current pause or equal to the length, I guess, right? Yep. Greater or equal. Nice. Consume. Where's the consume, and we could also just say consume number here, I guess, to be consistent. And consume number, which is gonna take a middle reference to self, and it's gonna return 64. Okay, I guess that makes a little bit of sense, does it? Like mute number, self-consume, yep, if is digit, number times 10. I mean, I think that makes sense. I think that's even more efficient than just storing the whole string in a buffer and then parsing it later. So that makes sense. Essentially, we now have a consume number function, which is not found because, okay, yeah, we just misspelled it. Consume number. Okay, cool. Is number start? Why are you not used anyway? Okay, because this method is not used. Okay, makes sense. So I guess we can try that out. For now, let's just create a basic program. Let input is gonna be, I don't know. Let's just try 7. See if that works or if we just get any good errors. So that looks inside our AST crate. Nice. So let tokens back new. Exactly. While we have a next token, we push this token into the back, and this has to be mutable. And we'll just print the tokens for now. Okay. Debug is not implemented. Let's just do that real quick. Drive. Yeah, we don't need all of that for now. Token kind also needs to implement debug and our text span as well. Nice. Okay. Yeah, let's see if that works or if we complete errors. Okay, number 0. Okay, but that worked. We get an of file token and literal is correct, end is correct, start is correct, but the number is not correctly parsed. Okay. Do we consume here? That's the question. No, we just say current char. Okay. Consume number. Okay, so maybe that's the issue, right? Because yeah, okay, makes sense. Because we incremented by 1 here, so essentially what we would have to do is something like this. No, that would be bad. No, we're gonna do that. We're gonna do something like this, and I guess now that should work, right? Okay, now we're unwrapping a none value because we're consuming current char. What do you use current char? Here. Okay, that cannot be the problem, right? Has to be in consume. It has to be somewhere here. Yeah, I guess. So we're just gonna move that to start, right? Let's see. Yeah, okay. Now that works. Cool. We're lexing our number. Next step. See if we get a bad token if we just do something like this. We should. Okay, just continue. Just adds that to the number as well, which is pretty dumb actually. Okay, I see why that's happening because we're consuming, right? And it is not a digit anymore, but now we have incremented the position. And because of that, our end is not correct here, and we consumed too many tokens, essentially. So I guess we have to peek here. Again, we can create a peek method, I guess. Peek char. Peek. Yeah, okay, let's just say we're gonna return here. I think that's gonna make our lives a little bit easier. And myself print char. And we're gonna ignore that actually. And we're gonna say that C is itself consume. And we can unwrap that. And I think that should actually fix stuff. Now we have to fix this. We can also unwrap that because we have made a bunch of checks before. I mean, that's really not that good actually. Let's just remove that. And we're gonna say return C map. We can map the char and just copy all of that in here. I think that should work. Doesn't it? Okay, now we have an option. Okay, makes sense. Okay, that works. Cool. And found option char. Okay, because this already is an option. Nice. Okay, I guess that should work now. And it still does not work correctly. Because, okay, that's not making sense. Consume number. Okay. Maybe we should not do that, right? We should consume here and yep. Okay, now we're running into an infinite loop because we are not consuming anything. If there's a bad token, we're not consuming that bad token, which makes sense. So if it's not, then we're just gonna say self consume. Nice, cool. And I mean, now we have to parse our plus and stuff like that. So we could say something like I guess we could say kind equal to self. How do we call that? Probably consume punctuation. I think that's good. So we're gonna create that method, consume punctuation. Right. Cool. Thank you, GitHub Copilot. Essentially, we can consume here without ever running into any issues. Okay, I think now we should even have a plus token. Cool, nice. White spaces are not currently supported, I guess. Because if I put a white space in here, we're gonna get a bad token. Yep, nice. That's cool. Next token. I guess we don't want to just skip white spaces in the lexer because maybe we're gonna need them later in the parser. So we could say else if self, or like see if self is white space, self-consume white space, right? And GitHub Copilot assumes that we don't want this white space in our tokens, but we do. So we're just gonna say self-consume and kind is equal token kind white space. Cool. So now we just have to create this method is white space. That's cool. That works. Nice. Cool. I think we're parsing white space now. Lexing white space now, right? Yep. Cool. Okay. I think we're finished with our lexer. If it parses that. Are there any bad tokens? No. Cool. So we have a basic lexer up and running. Nice, and it's not even that much code. So let me just take a zip real quick. Nice, that was fast. So I think we can say we've done that. Cool. Then next step would be to create a parser, which you have to include in here, probably parser. And what we also have to do is create an AST, I guess. Yep. AST. I mean, we could put that in the mod file because the module is called AST. So I just do that. Abstract AST. It's gonna be for now. Pop statements. It's gonna be a back of AST statement. And AST statement is gonna be structified here. And I'm prefixing that with AST because we're gonna have like different kind of statements later on. If we get into type checking and lowering to maybe, I don't know, LLVM, IR and stuff like that. Yep. So once again, we'll have a AST statement kind, so we can use Rust's pattern matching statement kind. And for now, that is just, we don't really have any statements right now. I mean, we have an expression statement, an expression statement, AST expression. Yep. I mean, I don't really like this kind of syntax. Do I? No, I don't. Yeah. Okay, though. Yeah, I do. Okay. So that's gonna be struct AST expression, and we're gonna have a kind x as well in here. We're gonna move that down here to separate statements and expressions. Kind, nice. And I think these statements should also have kind of a text span, right? Because we want to be able to also refer to these statements when reporting errors, but we can do that later. So we have this up enum AST expression kind. For now, we're just gonna have a number literal. Yeah, just call it a number. It's gonna be it for now, I guess. So we have this expression kind, blah blah blah. Nice. Now we have to kind of parse that, and that's where the parser comes. Abstract parser. Yeah. So we're gonna have tokens. Token. And yep, we're gonna have a pointer to the current token. And I think maybe we need statements, do we? Now we're just gonna build that the same way as lexer so that we have like a next statement method or something like this, like that. So import parser, pop it new as always. Correct. And we're also gonna create a method from input where we just create the lexer and push all the tokens. So correct. Nice. And the next thing would be to say and next statement. Just gonna take a mutable reference. Next statement. For now, we only have one statement kind. So I think here a peak method would make sense. Peak self offset. Right. And current also makes sense. Yeah. Next statement. And we're just gonna return option st statement. I think we can also safely import lexer here, so we all have all of those prefixes. Nice. Okay. Looks good. Next statement. So for now we only have an expression statement, so you just like, I guess we'll just say return parse statement. And parse statement. So what's speed of Copilot do for us? Nice. Okay, that's cool. If for now we're just gonna have an expression statement. I guess expression is a parse expression. And I guess we could also create constructors for these. So we say info ast statement new and pop an expression. Cool. Cool. So we're parsing an expression right now, which is not implemented. And then we just return some C statement expression. Parse expression. Cool. So we're matching the current token kind to private. Okay. I guess we'll have to make these public. I think that's gonna be a problem for all of those, also for the text span. Nice one. Okay, now these are public as well. Now we can match the token kind number, and we also have the number here. I mean, yeah, I guess. I guess we don't even need that. Can we lift the return out? Okay, cool. Parse expression. I mean, we don't need that right now. We're gonna need that later. So next statement. For now, we only have number statements, and I guess what would be pretty cool is a way to visualize our AST, because it is a tree and we like visualizing trees. Pop F. No, we don't need that. Okay, maybe we do. And visualize. That's also cool. Hmm. But I don't think that we want to do that necessarily. I guess we could also create an AC visitor. Like abstract AC visitor, which shows a reference to an AST. Exactly. Cool. Probably we could also probably make that a trade, right? Wait, I don't even know if trades can have implemented methods. I don't think that they can. AST visitor. I don't think that makes any sense. No, that does not make any sense. We're gonna create a trade for that. AST visitor. Visit number. See number expression. So I guess we have to create that as well. Abstract AST number expression. Cool. So we have this, and I guess we can create a accept visit. Visitor private trade can be private trade. Okay. Oh, nice. Okay, visit statement. Can we pre-implement anything here? Okay, cool. That works. Cool. Nice. So we have a visitor now, and what we can do now is we can create a abstract AC printer which probably needs kind of indent. I guess. And we're gonna have a method here. Impl AST printer print with indent and print with indent. Yep. I mean, that's pretty dumb. We don't need that because we can just access that right away. Okay, yes, that's cool. Number. Okay. So what do you complain about? Yeah, I don't think that's the case. Cool. And I guess we could also replace this 2 with level indent const level indent. Missing type. Correct. Cannot find. So we're just gonna put you here. Okay, cool. And now we can create a method here, which says, I don't know, visualize. And we just create a new printer and say visit. Cannot borrow is mutable. Okay. Why do we even need? Why do we need to? Do we need? Does this need to be mutable? No. Nah. Cool. And that's just gonna return nothing. Cool, cool. So we're gonna create our AST here. AST, C new. Let mute parser. This new parser here. I guess we can also just remove these prefixes, path specifiers. Correct. And now we can just say we can here print the tokens, and we can visualize our AST. I mean, that will not work for now, I guess, because it's broken. Okay, maybe that works. Did not quite work, I suppose, because it did not print anything. Okay, that's interesting. But we do have statements, right? Just debug that real quick. Statements. No, we don't have we do not have any statements. Oh, because you use new and not from input, which kind of makes sense. And from tokens. From tokens. Okay, maybe that will work. Okay, we're running into an infinite loop here. Because I see. Because that will not quite work. I guess we can say if token equals or token kind, we just return like if we reach the end of the file, we return none. Okay, so we have to implement partial equality for that. So we also have to implement that for our token kind and for our text span. Okay, maybe that will work. And it does not. But why? Wait, do we consume tokens? Okay. Yeah. Maybe we should consume tokens. That would be beneficial, I guess. So we don't say current, we say and soon. Yep. I don't think we need to clone here. Canada sign because it is borrowed. Yep. Okay, let's see. And we'll just say like self peak -1. Does that work? So we have to cast statue I size and have to cast this whole thing as a U size. Okay, that was too complicated. Soon. Okay, I think that should work. Okay. That's probably because of visualizing, right? Okay. Why does that happen? Let's see. C printer and we visit, right? So we say for statement, visit statement, and when we visit the statement, we visit an expression, and in this expression we only visit the number, right? So what do we do here? Huh? Okay. Does any of you guys see the problem here? Because I do not, genuinely. Let me just set a breakpoint here, I guess. Okay, so we're infinitely looping here. So, because, what? Okay, so that does not work. Okay, wait, let me Google that real quick. How to. So the problem essentially is that because we call visit statement here, we just call this method again. But like, I thought that if we set AC visitor visit statement, we did not call this method, but the let's say implemented method, like the overridden method. So let me just check that real quick. How do I call an can we use super? Does that work? No way. It's Java stuff, right? Okay. Yeah. I was confused, yeah. Because super is just a path qualifier. ChatGPT is lying to me. You're lying. Rest. Use default implementation of trade in override. Yep. This isn't possible directly now. Nice. Okay, yeah, something like a partial implementation. That's interesting. Yeah. Okay, that's also interesting. I guess we could also just say we do not provide this method. Stop. Because we don't want to re-implement that every time. Do we? Okay, now let's just create like kind of a default method here. So we're gonna leave that empty, or like not implement that. We're gonna say then do visit statement. Right. I mean, we can implement that, but you can also override it. do visit expressions of do visit expression. Nice. Okay. So now we don't say that. We say do visit statement and do visit expression. And now we should not overflow. Cool. Statement expression number 7. Okay, that's some cool, good progress, I suppose. So the next thing that we will have to do is essentially parsing binary expressions. So I think now we could try to parse something like this actually, because parsing something like this and something like this is like a whole nother difficulty level. Because something like this, you could just say, okay, I have a number here, okay, cool, or like an expression, and then there's an operator. Okay, let's just parse the next expression and see if it fits. And then just say, okay, this is our binary expression. As that would work, but if we have a multiplication, for example, we can just not do that. We can just say, okay, cool, we have a 7 here, we have +8, and this is one node in our AC. Because then we would compute 7 plus 8 first, and then take it times 9. But that's just wrong, because we first have to compute this part. And so we have to do that a little different. And we have to take a look at a concept like called precedence, operator precedence. Yep, and like each operator gets a precedence, and the higher the precedence, the stronger the binding essentially. So for example, if a plus had a precedence of like 2, and this asterisk had a binding or a precedence of like 3, it would bind stronger, and this expression would be parsed first. And that's how we are gonna do it, or parse our binary expression. So cool. So pretty far already. Now we'll try to parse it like this. I don't know what will happen if we just run this. Okay. Guess we will just not do anything. And that's fine. We do not need any error reporting as of now. And okay, so let's first define our AST nodes. So how should our binary expression look like? So statement kind expression. Okay. Okay, so we're gonna have a binary, and it should be AST binary expression, right? Abstract AST binary expression. And the problem why we're getting errors here, I guess, is because we have infinite size struct. So imagine if this struct would live on the stack. This struct would contain a binary expression, which would contain an AST expression, which would contain expression kind, which would could contain binary expression, and so on and so on. And that's why we get infinite size error, I guess, right? Has an infinite size. Yep. So we need some kind of wrapper around that to say that, or we don't want to store the value of that expression directly, but more like the pointer to this expression. So we use box smart pointer here, and now the error is gone away. And we also need a binary operator, I think. Right, so for now we have plus, minus, divide, and multiply. And nice, I think we're good to go. So we somehow have to parse that now. And what we can do to honor the precedence is we can, in this parse expression method, we will create another method called parse binary expression, which takes immutable reference to itself and precedence UH. Okay, that's fine. option AST expression. Actually, I think that's... I don't know if that makes sense to pass options here. Yeah, I guess. That's cool. It's fine. So option precedence, blah blah blah. And for now, we also need another method called parse primary expression. And like primary expression is just something like, for example, a function call, literals, like strings and numbers and stuff like that. And so we can essentially move this code right here. Right? And what we're gonna do here is we're gonna say let left self parse primary expression. And what we will do here is we're gonna say while we have to create a precedence method where we specify the precedence of each token. So we say while let some operator precedence is equal, like, while we have to create this method now, we say like current precedence, and say like operator token is gonna be self-consume. Right is gonna be a primary expression. Not exactly. It's not primary expression. It must be parse primary expression with our current precedence. And I'll get back to that in a moment and explain why that works. And now left has to be mutable because we now have to set left again. And exactly, it's the expression. So let's just create a constructor for a binary expression. Cool. So we call you, right? Nice. And in the end, we're just gonna return some left here. And I think that we need to think about this binary operator. I think it needs to be kind, right? And we'll have a struct kind and token. Yep, I think that makes a little bit more sense. Because we also have to like have the token reference to this operator, so yeah, we can later, for example, if there is invalid or if the operator is not defined for two types, then we can mark this operator, and for that we need to text span, which is defined in a token. Yeah. So parse binary expression operator. Okay, cool. Current precedence, and we now I don't think that we necessarily want to validate that this is a valid operator. I think we're just not gonna do that here. I think we're just gonna say, okay, operator, cool, but you're just gonna say token, because this is not part of parser. That's gonna be relevant later, right? Just do that. Let's just do it in the parser. I think that's fine. So we can just say event parse operator. And we need to consume here. Asterisk. And we can say operator, which token kind plus some token. I mean, that doesn't make any sense. We need a AST operator, binary operator. Parse binary operator. binary operator. Count, right? We have add plus here. So bam. Yes, I think that's also not the smartest way to do that, because right now we're gonna replicate the same logic, especially like which operators map to which tokens. I think about that. No, I think it's fine. I know how to do that better. So we're just gonna move this operator stuff out of here. Let's say let operator is equal parse self parse binary operator. Exactly. Now we're gonna try to say find sub minus. It's called minus, right? Kind map token is binary operator. Okay, so we have to create a constructor for that. Now we can create that token span, expected token found text span. We have to clone the token, I guess. Found token. Even if it's clone is not implemented for token, right? So where are you, token? So we need clone here. And we also need clone and text span and token kind then. Okay, nice. That works. And essentially, what we're doing now is we're passing a binary operator. And if we have an operator here, like if I guess we can say we'll unwrap the operator here. Cool. And while at some operator.map operator.precedence. Exactly. Cool. And now we have to implement this precedence method. Precedence. Cool. I don't know. Normally you would not choose numbers like this. I guess we can just say plus minus 0, 1. Multiply and divider 2 for now. That's gonna change if we get more operators. That's fine for now. And I guess that works, right? So we say parse binary expression while we have an operator. And I think what we're missing here is, I don't think we are necessarily, we don't need to check if the operator precedence. Okay, yes, we do. We do need to check that. If the operator precedence is smaller or equal to our current precedence, then we need to break. And essentially what we're going to do here is we're just going to parse binary expression with a 0. Okay, cool. I mean, we could just try that real quick. Move. What? Why just gonna dereference that. Type U8 cannot be referenced. Okay, you need to dereference that. Precedence found. Blah blah blah. Okay. What? Use of values. This function takes ownership of self. Wait, do you? No, you don't. What? I lost. Use of move value. Operator move to this this call to borrow the types content. So wait, this moves the operator? Type U8, okay, weird. No, why? Why are you moved? So we're using, wait, let me just recompile that real quick. Okay, so we're using operator move due to this method call and previous iteration of loop. Oh, I see. Oh, I mean that. Okay, that would cause some problems, right? Will it? Yep, that would cause problems because what we have to do is we have to parse this operator for every loop iteration. It just cannot stay the same. How do we do that? I guess we're just gonna do stuff like that, right? And take that. So, and then it's say just it's gonna be the operator, and let for the precedence. Okay, cool. I think that will work. And now we also do not have to unwrap you, which is cool. Yeah, that looks much better. Cool. So let's just try that out, and then I'll explain why this works, or at least should work in theory. So, okay, non-exhaustive pattern. Okay, we have to add this in our visitor. Self visit binary expression. No. Fn visit binary expression. Cool. I don't think we'll provide any. Okay, we could. We could. And we're gonna say visit binary expression. Binary expression. We indent. We print with the indent operator kind. I think we even have to debug here. We're gonna do that for now. So derive debug. Alright, cool. Can we run this now? Okay. We're still just parsing number 7. Oh, I see. Because now we have the problem that we have white spaces in here. Let me just try this without any white spaces. Yep. Okay, cool. So, this, okay, that's still wrong somehow, right? No, it's not. Okay, that's correct. Do you see that? You see this output? We have an expression which is a binary expression plus, and we say 7 plus 8 times 9. So in the order that it's specified. Okay, it's cool. And the problem is that we need to like ignore white spaces, I suppose. Okay. Self. Yep. So we just say we take tokens, and for now we can just say tokens. Wait. Ability. Yep. Essentially, exactly. That's what I wanted. Self new from tokens. I mean, that's just unnecessary. Because this constructor will not need that, and from input will also not need. So let's just change the constructor here, and for now we'll just ignore every white space. I guess that's fine. Yeah, cool, that works. So now to the explaining part. Why does this work? Okay. We're beginning with a precedence of 0, right? Which means that we do not have any operator currently. And then we parse a left expression, which is a primary expression. So in our case, it can only be a number. So in the case of this example, it's going to be 7, right? So I remember this example for a bit because I'm not sure again. Okay, so that's just going to be a number expression of 7. Then we say we try to parse a binary operator. If we don't find one, that's fine. Then we just do not have a binary expression. But if we do, we have to check the precedence of this operator. And if the precedence is lower than the current precedence or equal, then we also just want to return the alternative expression, so the primary expression. So in this case, the operator precedence of our plus is 1, which is greater than 0. So we say, okay, cool. We just go here and say, right is another, we can have another binary expression here. And I think that's not, oh, no, that's correct. And we can have another binary expression here, which would essentially mean that we pass the current precedence over there, which would now be 1. And we say, if once again, same thing essentially, we just try to parse a primary expression again, which is going to be the number 8 this time. And we try to parse another binary operator. If we do not find one, then we just return 8, which will be fine. But if we do find one, we find an asterisk, which means that we have a binary operator. And the precedence of the asterisk is 2. So 2 is essentially still greater than 1. So the precedence was passed. And so we just pass. So we know that we have to like bind the right side, this side stronger. And that means we can't parse another binary expression. I think that makes sense. Yep. And now the next thing to like think about is how will we handle parentheses, right? And that's actually much easier than you would think, because you could just say, okay, parenthesis is just another primary expression, right? You could say either that, which would not make too much sense. I think about it, right? Would it? Maybe it would, because primary expressions are basically like blocks which like just they are just basically one thing, right? If you take a look at that, that's not a primary expression, because it consists of like 7 plus and 8, which does not necessarily belong together. But if we say, okay, we have a parenthesis here, then we say, okay, this is one block. We can just group that together, right? And same thing would occur for like function calls, because if we just say something like this, it just belongs to this one thing, right? It just consists one thing, and that's why it's a primary expression. And I think that could work. So right now, I don't even know what would happen if we ran this. Okay, nothing. Which makes sense. I mean, the parentheses are lexed, so we can just use them. And so we will need another C node for that, which would be abstract parenthesized expression. And we just add that to here, parenthesize, nice one. And we'll also add that here. Cool. So let's try to parse that. So we'll go into here, and now things get a little more interesting. So now we say token kind, and we say left part, and we say parse expression, because in these parentheses there can only be another expression, and we don't really care which expression this is. It just has to be an expression. And then we consume another token, and we say, okay, it's not right, and then we panic. Which makes sense for now because we do not have proper error reporting, but if we do, we'll just report an error and not just panic because that's just not that user friendly. But if I'm not mistaken, that should work. Okay, makes sense. Expression. No, that makes no sense. Self visit parenthesis expression. AST. Wait, did I? Oh, I forgot the AST prefix. Okay, and now we have to also add that in the printer. Visit parenthesis expression. Okay, cool. I think that should work, right? And it did not. Okay, why does it not work? So once again, it would mean that our statements are empty, right? Which means the next statement would return nothing. Which would happen if we didn't return anything here. Which would happen if we did not, if nothing matched here. Okay, that's weird. But it's called a left parent, right? Okay, left parent. We're starting with a left parent, so we should that should theoretically should work. So let's just debug that real quick. See what we get here. Kind left parent, right? So we also get it here. Okay, so we're parsing another expression. Ah. So let's just see. Would that work? No, it wouldn't. Okay. Let's just debug that once again. So that's correct. We have a number expression. We have a number expression? What? Why do we have a number expression? What the? That's not. Okay, that's correct because this method was entered from within the parenthesized stuff, I suppose. So let's just say another breakpoint here. Why do we go into this method so often? Okay. That's weird. That's genuinely not quite the behavior I expect. Did we forget to consume somewhere? We're consuming here. Press expression. No. Okay. That's not how this is supposed to work, to be honest. Okay, let's see. What happens when we step one further? We get an expression 7 once again. And I guess once again here. No. Now we have an 8. Which does not make any sense. If you think about, okay, maybe it does because we're just calling parse expression even on our binary expression. Yeah, right. So we have number expression, blah blah blah, and once again we go into here. Now we have 8 again. Parse binary operator. We're consuming here, right? Wait, let me just. We can take a look at the current position. Okay, so we're currently at position 2, which means we have consumed our. Right, which means we have consumed 7 and the left paren, which is correct because here is 7. So the next thing to do would be to say, okay, we parse the binary operator, which does not happen. Why? Okay, so where do we go here? Step into, you know. Okay, so we're saying parse binary operator. Okay, now we're at the right parent. Which means that this is probably gonna be none or something. Right? Okay, so now the stack just unwinds. And left is 7, hopefully. Nice. Yep. Right is gonna be 8. Okay, that's correct. And now we're gonna return. And now what is left? Left is binary expression, okay. Yep, plus and token, that's correct. And why are we in here again? Okay, but our current position is great. Okay, so now we are here, and where do we go next? Okay, next we go here. And this is binary expression. Oh, no, we did not panic, right? Okay, I think we might have just panicked. Why? Okay, so the AC does not have any statements. Something is not quite correct here. I don't see what exactly right now. Blah blah blah. Parse a primary expression. Okay, that's fine. So let's just try to step through this and find out why this could happen. So, where do we start? So, when calling this, we call parse our expression. We say, okay, cool. You parse our first primary expression, which will then eventually be because the first token kind is a left parent, we will step into here, which will result into another call to parse expression. Because we have consumed the token here, we now point to 7, right? So because we now point to 7, we call here with 7 and we say parse primary expression. Which will result in another call to here, which should eventually evaluate this piece of code because it's a number, right? And then this will be 7. We'll pass the binary operator, which then should result into a this. It should get token and plus binary operator. So the precedence will be 1. Because the precedence will be 1, the precedence will be greater than 0. So we go into here and say, okay, right is parse another binary expression, which will be, it should result into 8 being evaluated, being parsed as a primary expression. And because I think I see the problem. The problem is that once we have evaluated 8, parse 8, we're going to here and say self.parse binary operator. And in here we consume the token, but because the token is not a valid binary operator, we still have consumed it, right? And because we have consumed it, we now point to the end of the file and not to our not to our right parent. And because of that, we get an error. So what we have to do here is we have to say peak current. Exactly. And now we have to say self.consume. See if that works now. Yeah, okay, cool. Wait, why is it not printed as a parenthesized expression? Did I mess something up with our visualizer? Visit parenthesized expression. Visitor. Should print parenthesized expression. Okay, what would happen if it did that now? Okay, that works, but it's just in the printing. Why? What? Wait, am I returning? Oh, that could be a problem. We're not returning a parenthesized expression. Yep. ASC expression parenthesized. Correct. So now we should see that. Right? Cool. Okay. So that is working. Now what we can do is, yeah, we can say we're just gonna create a little evaluator which just evaluates the AST. So nothing too special as of now. Abstract AST evaluator. So this will not get an AST. I don't think we need any of that, do we? Okay, now we need a last result. Last value, right? Which is just gonna be option. What's it gonna be? It's gonna be option like I64. Impl AST visitor for that. Visit number, last value, some number value. Correct. Binary expression number. And we're gonna visit self-visit expression left, and we're also gonna visit right. Cool. And why do you like us not covered? Okay. Multiply and divide. Cool. So essentially we could get a result now. So we're gonna say that eval, I think we need constructor. Oh, eval is AST evaluator new. And we're just gonna say eval, no, AST.visit mute eval. Okay, declare it as mutable. Okay, cool. Now we probably, no, it's not need to be public. Does the, okay, it can be. Don't really care. Result, okay. Last value. Let's see, what should we even get? We should get 135, right? Yeah, okay, that's working, cool. So we have a basic parser, we have a lexer, and we have a AST evaluator. I think that is pretty good progress for our first stream. I like that. That's cool. Yep. I mean, I think I'll just commit that. And we're gonna be happy. And it's pretty good progress. So one last thing that I want to do is I just want to quickly think about what we're gonna do next stream. So essentially, roadmap. That's what we want to be able to, and we did that. We are able to evaluate expressions, right? So let's just see if we can run this because we did not test that. What should this evaluate to? Okay, that's a good question. Okay, that's a bit. I don't know what's 37. Okay, it should evaluate to minus 164, I guess. Okay, it's 2. To be honest, I don't think that's quite correct. So, okay, maybe we cannot end the stream as of now. I think we have to fix that. Okay, let me just get the calculator because maybe I'm just dumb. Okay, it should be 7 minus 180. No, 48. 100. Okay. 7 minus 148 is minus. Ah, okay, so I was correct. Minus 141. I think I said that right. No, I said 47. Okay, almost. Why do we get 2 here? So is it the AST correct? It's a good question, actually. So, my expression, that's correct. So, okay, what? Okay, that's wrong. That's just not correct. So, it still would not explain that. Okay, weird. I mean, that's correct. That's correct as well. And that's just terribly, utterly wrong. It's just not correct. Why? Okay, that also explains why this is 2, because it just fills this expression once again and says, okay, you're 2, cool. Why though? Why would you do that? Do we? Okay, I think I see the problem. Because we break here if the precedence is the same. We just return. Okay, that could definitely be the issue. Let's just see if that works. Yep. Okay, that was the issue. because we broke out of this loop too early. Because our divide and multiply have the same precedence, and so we broke out of the loop here. And at this time, left was our left expression, like everything to the left of 2. And that was bad, because then we just returned everything to the left of the 2, and we treated 2 as a separate statement, which is not correct. And now we don't do that anymore, which is pretty cool. Now we get to correct result. Okay, so now we can plan what we're gonna do in the next stream. I don't know when the next stream will be. Next stream. So, roadmap. The roadmap consists of milestones, consists of code snippets that we would like to be able to run. Next stream, okay. So I think what we're gonna do next stream is, we could probably introduce variables. I mean, variables are not that complicated, so something like let x, let y, let z, and z is gonna be x plus y, something like that, right? Maybe even 30 times 8 minus 1, something like that. I would like to be able to run that. And I mean, what else could we do? Maybe, just maybe, we could get into, I don't know, want to do functions as of now. Maybe we could do something like an if. So like if, no, we don't want to do that. I think first of all we want to probably do let's support for let statements. We want add error reporting, and maybe add if statement. Okay. Add support for basic arithmetic operations. I think we did that, right? So next stream we would be able to do that. Cool. And I also indent that. Cool. Nice one. I think that's the plan for the next stream. That we add support for let statements, error reporting, and maybe if statements. Something like let I'm sure if we want to do like have mutability by default. I think so. And I really like Rust's approach to like have let for everything, and you can just say let mute. I mean, that's cool. Like this, and we're gonna say x. I want to be able to do something like this, I guess. Yep, I think that's it. Pretty cool stream, I guess. Yeah, so thank you for watching. Thank you for watching on YouTube. If you watched until now, I appreciate that. Leave a like, subscribe, and see you next time.